This is the main place you want to go for finding information on the web pipeline. So what you're looking for is if you scroll down to the bottom of this main page, at the bottom here, there's this section called Data, and that has a number of different sections within it, both getting started with web data and other things as well, calibration status, known issues, etc. As I just mentioned, JDocs is our main documentation site. Start there if you want to look up information. This provides you with both an overview of the pipeline. It has all the information on the data products that I've talked a little bit about today, talks about any known issues, calibration, etc. And I'll walk you through some of that in a moment. There's another documentation site as well. This is the so-called Read the Docs site, which is the kind of site that's often associated with many Python packages. This is where you should go if you want details of specific code steps. So if you want to know exactly what algorithm is used in the flat field step or in the flux calibration, what are the extensive list of input and output parameters that you can try modifying for the step, this is the documentation site that you're interested in for those kinds of details. But for starting off with, what is the pipeline? How do I use it? What does it do? Start here at JDocs instead. And we cross-link back and forth between them. So if you read through the JDocs site and you find a link of a particular pipeline step you want to know more about, we'll link out to the Read the Docs site from there, so you can follow one into the other, depending on what kind and extent of information you're interested in getting. This is the JDocs site that I had up just a moment ago, this data section down at the bottom. Here's a few of the different sections in data. I've kind of tried to annotate them with what they are. Hopefully they're fairly straightforward. For this one at the top, getting started with web data, that's obviously a good place to get started. If you're just learning today for the first time about the web pipeline, that's a great page to start with. We'll provide an overview and a list of where to find the information that you might be interested in. If you want to know how to get web data, there's this page here on accessing web data. That gives you the information you need to know about actually downloading it from MAST, either by web interfaces or by some kind of Python programmatic interfaces. Actually, even via Amazon Web Services as well can do that kind of interface. If you want to know more about the pipeline, that's in this section, Science Calibration Pipeline. We list the pipeline steps and algorithms. So all those things I skipped over an hour or so ago, saying I wasn't going to go into detail as to how these steps worked. If you want to know how they work, go here. It'll list them out and it'll link you into JDoc and to read the docs as necessary for more details. This option here, Operations Pipeline Build Information, that's where you get the latest updates on the pipeline. So what's new? What did we change recently? What is the latest build? That's a good place to keep an eye on for that information there. Likewise, if you want to know how to run the pipeline, how to find the pipeline notebooks, or this kind of catch-all option here, tips and tricks for working with the pipeline. Loosely speaking, that's useful stuff that I need to keep looking up, but I want to keep reminding myself about how to do. And in a couple minutes, I'll touch back on some of those examples as sort of advanced topics. The other key things here that you want to be knowledgeable about is these two sections, calibration status and known issues. So if you're working with web data and you want to say, now, how good is the flux calibration? How good is the wavelength calibration? I see an outflow at 50 kilometers a second from my galaxy. Can I believe that 50 kilometers a second is your wavelength calibration that good? Here's the page that you go to find that information. It's broken down into individual instruments and then into individual modes. So if you're working with MIRI MOS data, cal status, MIRI MOS, that will tell you how good the MIRI MOS wavelength calibration is. Likewise, if you're interested in knowing about how good is their absolute flux calibration, there's a page on that. If you want to know calibration information, here's the page you want to find it from. The second page you want to be particularly familiar with is this known issues page. So this is where you can go to find out, now, what weird stuff is there in web data that I need to be aware of, and why might I want to reprocess web data for a given science program. As above, this is broken down into various different instruments themselves and different instrument modes under that. There's some things that are common across all instruments and others that are very specific to, for instance, only MIRI coronography needs to worry about problem X. So that'll be on the MIRI coronography page. So click through these pages and it'll tell you more about the kinds of things to watch out for in your data, what they look like, and most importantly, how you might want to change the pipeline configuration in order to improve what that data looks like for your own science analysis. So what I thought would be useful to do now was to try talking through just a couple of those examples. So two of the issues that affect almost all web data, what they look like, and these cases, why you might want to modify the pipeline in order to deal with that data. This is information that you'd find on the known issues page that I was just talking about. Two very common ones you'll see there are either large cosmic ray artifacts or the so-called 1/f striping noise. We'll start actually with the second one first. So 1/f noise is a correlated noise in the readout amplifier that causes striping in the data. So these are electronic systems, there's noise in the readout, and it persists over long enough times as you're reading out from the top to the bottom of the detector. There's a long period variation going up and down in terms of what that noise is. And if you map this into 2D space, it looks like striping in the data. So here's an example of, I think this is a NIRCam dark file. So it's a observation we took where there's no light from the sky getting into the detector. So all that you're seeing is this striping noise in the readout. And you can see this very strong banding over the detector from this noise. There's a correction that we make available in the pipeline now in order to fix that. So this is the so-called clean flicker noise step in the detector 1 pipeline, and the options to turn on this correction are made apparent in the notebooks I was working on. So in this particular case, for instance, it can do a good job of taking this very striping looking data and turning it into a very smooth observation. That's just a dark frame, for instance, so let's look at an actual science example. Here's a couple science cases. There's a NIRCam imaging case in a very rich star field here to the left, for instance, showing you, in this case, is blinking back and forth between the regular data and the 1/f cleaned data. So you can see how you get this striping pattern in the original data and how it largely goes away in the destriped data. Likewise for NIRSpec, here's an observation of NIRSpec multi-object spectroscopy. Each of these different lines here are the dispersed traces of many different objects in your field of view. And you can see these strong vertical bands of striping going across the detector. This is that 1/f noise. And so if you were to look at the spectrum of your object, you might see either emission or absorption troughs in your object spectrum that aren't real. They're just due to this striping instead. Then on the right here is what that looks like after we've done that cleaning, where it's much reduced in terms of the size of these artifacts on the detector. This isn't something that Pipeline does by default. If you download data out of MAST, it will be stripy to some degree or another. This is a correction that you'll have to run for yourselves at the moment. The main reason why is because how you do the correction is going to be very dependent on your individual science scene. So are you working with a very rich star field like this? Or are you working with a very sparse field where you've got very deep data at very high redshifts that isn't that much flux in there? Likewise, are you working with something where there's lots of spectra all over the detector or just 1 or 2 sets of spectra? The algorithms that you use to improve one kind of data are not the same as you'd use to improve another. And if you use the wrong algorithm, you can make the data look worse. So there's fairly extensive documentation on the JDocs page with, for this kind of data, we suggest that you run the step with these parameters, etc. And there's a lot more examples there that you can try looking at where if this is something that's important for your data, here's how we recommend reprocessing the data in order to be able to deal with it. But tweak things around. You'll have to use scientific judgment to tell what looks best for you and what is it that gives you the best science data products. The second general case we see in a lot of data is, well, for the near-infrared, it's called snowballs, but these are very large cosmic ray events. So I mentioned earlier, cosmic rays break up our ramps so that we need to now fit before and after these cosmic rays disrupt our ramp in order to get good slopes for each pixel. There's actually a different kind of cosmic rays as well that cause really big features on the detector. So they can cause, in this case, this very bright saturated core of pixels, and then kind of an extended halo of fluff surrounding it as well. So these cosmic ray events can affect tens, hundreds, or in some cases even thousands of pixels on the detector with these artifacts. So here's kind of a zoomed in image and some NIRSpec data on one of these. Then here's a zoomed out image just so you can see how there's lots of these little blotches all over the detector. This is something that we've been gradually making progress with time over the various different pipeline builds in terms of how well we can find and remove these features. So you can see, for instance, between build 10.0 and 10.1, we managed to take out the halo of this object pretty well. And then in 10.2, we managed to take out the saturated core of this object. So it now looks much cleaner, both zoomed into this one feature and also in general for the many features over the field of view. At this point in time, most of these large blotchy cosmic ray snowballs are pretty well corrected by default in most near-infrared data that you're likely to work with. It's good to be aware of what they look like, though, so that if you see any that break through the default corrections, then you can find some guidance in terms of how you might want to tune the algorithm in order to help suppress them in your specific data. The mid-infrared is much harder. So what we call cosmic ray showers are the mid-infrared version of snowballs from the near-infrared. From the near-infrared, then you can see mostly things are circular. They've got a big saturated core, a big circular halo around them. In the mid-infrared, things are blotchy and weird and very hard to measure. It's weather, so it changes a lot over time how many cosmic rays and how many cosmic ray showers affect any given program, and it's largely luck how bad it is for any given set of observations. So some observations, for instance, get lucky and have very few showers. So here's a fairly nice clean observation of the MIRI MRS detector. Here, the vertical striping that you're seeing is the actual dispersed spectra themselves. These little tiny white dots are just regular cosmic rays that we're seeing. But in this case here, these giant white blotches you're seeing over the detector are these cosmic ray showers. Those are very hard to correct with the pipeline. As I showed you earlier, that nice ideal case jump of a cosmic ray where you had a ramp in the pipeline, and then it jumped up, and then it continued increasing again. Here's what a cosmic ray shower looks like. It's got an original ramp, it jumps up a lot, and it keeps going up in some gradual curvature and asymptotes to some slope that is different than your original slope. What that means is it's incredibly hard to actually find and flag these in a general sense now during the Detector 1 pipeline. We're making headway on dealing with this, though, and that's something that's been changing a lot over the last few months. So on the left here is a pretty bad case of cosmic ray showers in the mid-infrared, and what we got with the latest released version of the pipeline here. There's still definite blotches left, but the amplitude of all of those has been dialed down. And we're hoping, in the latest thing that we're working on at the moment, we can actually go from this case to this. So here we're able to do a much better job of suppressing all of these blotchy cosmic rays that cause problems at low surface brightnesses in data, and have something that looks a lot cleaner. We're still in the middle of working on testing exactly how this works, so we're hoping that this will be coming out in a version of the pipeline that you can see soon. It will be something that you have to run for yourself, as it's going to be very scene dependent in terms of whether or not it helps you with the data or if it introduces artifacts. So this is a great example of something that might make a big science impact to run for your specific science case, but isn't something that's in the general pipeline. That's a reason to run the pipeline for yourself at home. So time's getting on, but I think I've only got a few slides left at this point in time. So I wanted to kind of wrap up by talking about a few things that have changed in the pipeline recently and kind of where we're going in some of our future development. These are incredibly abbreviated lists. Obviously, there's a large number of things that we work on in any given pipeline version. You can always look at JDocs to find the complete list. But for anybody who's been following along, running the pipeline for yourself already and wants to know what's new, some of the things we've fixed lately is in build 11.1, which is now the past build, the just before the most recent one. Then this is where we added that 1/f correction step to Detector 1. So that's fairly new, actually. That's something that's now available to process through on your data that wouldn't have been available last year. We've been making lots of improvements to the runtime and memory management of the pipeline to make it easier for everybody to run at home. So we've been helping to identify all of the tall poles in runtime, the tall poles in memory management, and really kind of beat those down so that it's possible for everybody to run the pipeline at home effectively on the typical laptops that most of us have. and we'll be making a number of improvements to individual modes like nearest and nearspec as well. Likewise for 11.2, this one 11.2 is the latest one that we're just now installing into MAST. This is what we're using to now process all of the data that you would find out of the MAST archive, where we've made a number of improvements, things like nearspec outlier detection. We're working on nearspec MOS and wide field slitless data, and fixing a variety of bugs that occurred in the pipeline. Things to look for soon. Also a very abbreviated list, but one of the main ones here is that top one that I just highlighted on a previous slide about some potentially big improvements to how maybe MRS cosmic ray showers are fixed, which can make a big impact if you're looking at very low surface brightness observations. Likewise, further improvements to the pipeline itself, actually, memory and runtime usages, and trying to get into a bit more in terms of advanced methods to do with better spectral extraction. Pipeline started off fairly basic, do a straightforward extraction that's easy to code, easy to understand. But now that that's working, we want to start moving on to more advanced things where you can do a better job of pipeline extraction if you use things like our knowledge about the point spread function on the detector. If you want to find out all the information about the things that we're working on now and some of what you can look forward to in the coming months, here's the link where you can go to monitor that information on the pipeline page. One final note I'd make on folks that are interested in advanced topics, there's this page on the JDoc site that you might be interested in taking a look at. It gives some examples of ways you can really start doing powerful things with Web Pipeline and customizing it for your particular case. This gives you information, say, about if you want to start working with intermediate data products and work with non-resampled IFU images and really get as close to the data as possible. There's information here on how to access world coordinates from those intermediate stages. There's information on how to create custom pipeline steps. So if you say have a different way that you think you'd really like to do snowball correction, or a better way that you think you want to do a stray light correction that would work better for your own data, you can create your own pipeline step and insert it into the notebook. So if you wanted to add something between the flat field and the photometric calibration step, you can add your own step that does whatever it is you want it to do in there. And there's some examples on this page that allow you to do such advanced things as well. Then finally, I'll just close with this slide. Obviously, I'm happy to answer any questions that people have now, but after this session closes, here's how you can get more information and stay up to date on the latest news. The two things that we particularly suggest is, first, subscribe to this JWST Observer news page. Here's where we send out announcements to the community every so often about big things that have changed. We announce every time there's a new pipeline build available there, so you can update your pipeline and reference file versions. We also actually announce there oftentimes other things as well, like major improvements in steps, things like the call for proposals, a variety of various different topics. You can also subscribe to getting reference file updates as well. So when we make individual updates to reference files, you can get notified they're available. They might not be used by default until the next pipeline version is released, but if you want to stay on the bleeding edge, that's one way that you can stay up to date with exactly what we're doing. If you have questions about either your data or the pipeline, step one is to check JDocs. I pointed you at a couple particularly important parts on there, particularly known issues. If you're seeing something weird in the data, look at the known issues pages and see if there's some description there about why it might look that way and what you might want to do in order to try and fix it. If it's unclear, you can always contact the JWST help desk. There's a link to that here. Or if you just want a little bit faster feedback, we actually have office hours every 2 weeks or so. And that's a WebEx call similar to this one, where you can call in and there's a panel of experts there and you can essentially show us a plot. Say, hey, I got this weird thing in my data. Do you know what it is? And we'll be happy to help you dig into that. And can point you to resources and help you figure things out as necessary. And finally, I'll just say, if you have a suggestion on, I think the pipeline should really be doing this instead. The pipeline itself is open source and pull requests are very welcome. We're happy to work with folks in the community who are having issues both with their own data in order to help make the pipeline itself better and better serve the needs of the science community to do the science that we're all interested in doing.